Okay, on my phone. Okay. Here we go. We're live. Only 20 minutes later. All right. What are we looking for? All right. So today, let's just start talking about new material. I'll feel better. So last time we were talking about optimization. Okay. So in optimization, we're mod 7, right? This is the last thing that's on the exam. Click, 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 click. You know you're not going to open, are you? Okay. We went over homework 6. We went over optimization. So let's talk about optimization. You have a main idea and a constraint. Okay. So you would have something like this. So you have, if you're trying to, I'm just going to do the home. I'm going to go over the homework. Because I don't have examples there where I want them. All right. So I'm just literally going right into the homework. So here, a 3-sided fence is to be built over a river. Okay, here's the picture of it in the homework. There's a picture. The blue part is the river. The X is the length and the Y is the width. Okay, length times width would be area. So X times Y is going to be the 200. That's what this right here says. Area equals X, Y equals 200. So I could solve for Y and I could say Y equals 200 over X. That's a constraint. I'm constraining Y. Then it says find the minimum perimeter. So the perimeter is equal to 2x plus y. Does everyone see that? There's an x, a y, and an x because you have 3 sides. So 2 x's and a y. Okay, so that's the perimeter. And then it says, okay, that's a function. Let me just write this. That's a function of x and y. But I can't put that into Desmos. But I mean, Desmos isn't going to graph that 2-dimensional function. What I can do is write the perimeter only as a function of x by replacing the y with 200 over x. Now I have 2 equal signs. Now I have something I can graph. So let's turn this image off. And there's the graph. To find, and what's the minimum perimeter? So that would be right there. That's the minimum perimeter. So x is 10. So you see that? I don't have to do, I could do the first derivative test. I could do the second derivative test. I could spend all day processing the fact that all I have to do is click on that thing. I'll find the minimum. Okay.
Professor, is there a way we could see the board?
Would you like to see the board?
Yeah, I would.
I would certainly like you to see the board.
Thank you, Professor.
Okay. Can you see it now?
Yep, we can see it.
All right. All right. So you didn't see the picture before, so let me show you the picture then. Here was the picture of this is a picture of the setup. It's just a stream with an X, a Y, and an X, and the area is 200. Okay. So, all right. So that's, once you find it, you have to answer the question. What does the answer say? It says find the minimum perimeter and the dimension of the corresponding, the dimensions of the corresponding. So we know X is going to be 10, right? So there's another, so 10 times what gives you 200? You have to go 10 times 20. You have to go back to this original Y equals thing that you used to get rid of Y and put the 10 in there. All right. So does everyone understand that there's a main idea, it's perimeter. It's a function of multiple variables. And they give you a constraint that allows you to get rid of one of the variables. That's all we have to do. Once we have it in terms of one variable, we could just throw it into Desmos and use all the properties we were using before. All right, that is an optimization problem. Okay. This question number 2, let me fold up question number 1. Question number 2 is slightly different. Okay. I think we talked about this. You want the distance between a point and a curve. So the distance between points, distance formula is the square root of, between 2 points, between, let's see, x1 comma xy1 and x2 comma y2. Okay, so you have 2 points and you want to know the distance between them. You're using the Pythagorean theorem. Okay, the Pythagorean theorem says that x squared plus y squared equals z squared. Okay, in this case, the x is the distance between the. Okay. I don't know what happened to my screen. Okay. The x is the distance between the x's, so it would be x2 minus x1. And the distance between the y's would be y2 minus y1 squared. And z is just the distance between them. The Pythagorean theorem, you know, it's x and y, and you just the distance between them. So that's the formula. Now they're telling you one of the points is 0, 4. So 0, 4 is one of the points. Okay. And the x and the y are coming from the graph. It's the distance between those points and the graph. The graph points are just going to be x and y. X and y. Okay. Except that now, if I put the d squared in front, let me just put it here. D squared. That's a function of 2 variables. It's a function of x and y. So I have to find a way to get it in terms of one variable. So, and by the way, if you're not happy with the square, let me take the square. I wouldn't expect you to be happy with this. It doesn't matter, but you can have, I'm just going to put this in there. So it's the square root. That's the distance formula like that. Okay. So I'll get rid of this. All right. So how do I make this only a function of one variable instead of 2? Anyone? I need to get rid of the x or the y. Which one do I have an equation that tells me what y is? This is the curve right here. That's the curve. The X and the Y are just points on that curve. So that means Y equals 19 minus X squared. That's what Y is, right? So I'm just going to put that in here. Okay. Now I have the distance function, and now I can minimize it. Okay. Just want to wrench thing here. It's okay, I just adjusted it so I could see it. So where's the minimum? So there's two of them, one here and one there. So the minimum value is X equals this number. And then Y equals whatever. Okay, Y is H of X. So if that's what X equals, then Y equals H of that, which is 3.4, whatever. So there's the X value and there's the Y value. Okay. On the curve. There's another answer with the minus. So there's more than one answer. It's just find the points. The other point is the exact same point, except yeah, the points look like this. Let's see, it's that, 9, 7, 3. And the other one is this minus that. Okay, those are the 2 points. All right. Any questions on that? So, do you get the idea though? So it's just a matter of having a constraint. All right. I'm gonna let you do the other ones, but here this Norway window thing, the maximum ladder length is given by this formula. This is a stupid question. I didn't pick this question, nor would I ever put this on a test, because literally they tell you the maximum ladder length is this. They're not showing you at all where it comes from, just telling you what it is. All you have to do is plug the A and the B in there and it's done. It's a nice question, but how they get the answer, it's just a formula. Okay. I think I talked to you about this one. I really like something like this. This is too easy. You just click on it, bloop, and you find the minimum. It says find the X value that maximizes the revenue. So that one's super easy, just tough to find it. I have to adjust the window to find it. It's somewhere over here. Okay. If you just hit home, it pops up there. It's even easier to see now. It's right about there, 12. Okay. In T hours, a worker makes Q items, find the time at which the worker's efficiency is maximum. So that's just the derivative. So you're just going to graph the derivative. Okay. Oh, capital Q. Sorry, my bad. Okay, and then you just have to find the maximum derivative, which is going to be right there. 5. Okay. All right, now so are we okay with that? Those are all the basic questions. There's one or two others you can do. I really like this one though. I didn't see it because I skipped over it, I think. The sheet of paper one, question number 2, is a personal favorite of mine, and it frequently makes its way onto the test. Okay, so we're taking a piece of paper and we're cutting squares out of the corner. Okay, so cutting squares out of corner. By the way, the solution, I think, has a picture. So let's take a look at the picture. The picture looks like this. So there's a piece of paper and we're cutting the corners out. When we cut the corners out, they're gone. We can fold them up and make a little box, right? Can you picture that? The corners are gone. These are the sides. Okay. So then all you have to do is understand that by you're making constraints about, so the main idea is the volume. Volume is a function of length, width, and height. Okay, and it's just length times width times height. That's it. But now I only want it in terms of x. So I can constrain each one of them. The length is going to be 78 minus 2x. The width is going to be 76 minus 2x. And the height is going to be x. Okay, once I have that function, I just have to put it in and have it graphed. Now, when I have it graphed, you have to ask yourself, what am I seeing? What am I seeing? I don't know. What do I need more of to make this visible? What do you think is going on here? Well, zooming in, I want more y value. Do you see, I want to see more higher. Because I don't know what this function does. It seems to go up and then come down and go up or do something. So let's go into the wrench and make the y value bigger. And by the way, if you just type in 9, 9, 9, 9, 9, eventually you can see it. There it is, right there. So it'd be just a maximum and then it has a minimum. Which do we want? Do we want the maximum? Do we want a maximum volume? Or do we want a minimum volume? By the way, if you cut 38.5 off of a piece of paper that's only 76 wide, it's going to be a negative number, I think. So that's probably not what we want. We probably don't want that minimum. Okay, how much could we cut off? Could we cut off 12? If it's 78 inches wide, can you cut 12 off of both sides? 24, you could cut off that. You could do that. So that must be the answer. So this must be the maximum volume, and that's what x is. Okay, that's not to say it's the length or the width. Actually, it is the height. That's the one thing it is. That 12 is the height. If you want the length and width, you have to plug it in and find out what they are. Or you can do it by hand. That's all it's done by hand there. Okay, I like this, and I like it because if I said any piece of paper, if it was at 8.5 by 11, you know, that's a regular piece of paper, right? 8.5 by 11. Okay. Again, all I have to do is make sure I can see that maximum. There it is. So 1.5, if you take a piece of paper that's 8.5 by 11, that's a regular piece of paper, and cut, looks like 1.5 inches of squares off of each corner and fold it up, you'll get the biggest volume. And the volume will be really 66 cubic inches. That seems pretty big. Do you understand if you take too much, if you don't take anything off, it won't have a volume, it'll just be flat. So the less you take off, the flatter it is. The more you take off and bend up, you get all this height on it, but it gets long and skinny, and the base gets small, so then you won't have any volume again. You're like a long, skinny vase. Okay. All right, that's enough of these. Can I move on to the next topic? That was just what we went over last time. The next topic is going to take us to the rest of the semester. I want to do it now because I want to put the easier part on the midterm. The harder part you'll have on the final. So what is the rest of the semester going to be about? Okay, so what is calculus?
No. The study of
Math is a language. Maybe I'll do my asking now. Since so many people are here, let me just ask. Okay. Talk to me, Slade. Slade here? Is this the wrong class?
It's the wrong
Oh.
clocks.
It's the wrong class. This whole time I've been in the wrong class. Oh, because I have more than one of these openers. Here we go. Is this your class? Yes. All right, lesson 7. We go, class discussion. Stay on. I really need to know this. What is calculus?
The study of change.
It's the study of change. Is Kara here? Kara's not here. Mahir, what are the 2 rates of change? Your question's too hard. What are the 2 rates of change? Mahir, you're here.
Average and instantaneous.
Very good. Average and instantaneous. So we've been studying change, right? And so when you're in your real life job, you could be, you might want to talk about average rate of change. You might want to tell your boss how quickly you're on average, how productive you are over a period of time. Or you might want to talk about how much money you're making on average over a period of time. Or you might want to talk about right now, the instantaneous rate of change. Okay, so we did all this stuff to find the instantaneous rate of change. To find it, we invented limits so we could find it. And then we found it. And then we had all these quick and dirty rules that we used just to find it easier. And then when we did that, we had all these applications, including optimization, finding the max and min as an application of derivatives. But other things like Newton's method and L'Hopital's rule. And L'Hopital's was actually using derivatives to find limits. So we could find more derivatives. Okay? So that's the mess quagmire we've been in this whole time. Where are we now in this story? Well, you got to know something. Whenever we invent something in math, like arithmetic, or addition, we invent something that undoes it. So what undoes arithmetic or addition? What undoes addition? Subtraction. Yeah. What undoes multiplication? Division or factoring, depending on what you're multiplying. What undoes a function? Like sines and cosines. Inverse sines. So what undoes a derivative? Oh, we invented derivatives. Actually, by the way, you wouldn't undo a limit. There's something we don't undo. We don't be like, as x blows away from something, we don't care what happens as it blows away. We care as it heads to something. But when we find the derivative, can we undo the derivative? And yes, we can. We can undo the derivative. All right. Let me just finish these attendants here. Nana, you're here. What's the relationship between position, velocity, and acceleration?
Velocity is the first derivative and acceleration is the second derivative.
It is. And so now, Nana, if you want to go backwards, suppose you have the acceleration. Like, for example, we know how quickly things fall, and we know the acceleration of gravity. If we want to go back and figure out where something is based on it's something's position, we're actually going to go backwards. We're going to undo the derivative. And so that's why we're like all of a sudden like, oh, okay, so if we have acceleration, we can use undoing of the derivative to find the velocity and then to find the position. Okay. Anusha's not here. Melanie, not here. Because these don't really relate to my discussion. Suhavi's here.
Hi. 0 times infinity can be anything.
zero times infinity could be anything. Anusha, what does the mean value theorem say? I see you're here. You weren't here. Go ahead.
Hi. The mean value theorem says
It's an application of derivatives. So there's a derivative and there's what else? Nope. Are you with me, Anusha? Mean is another word for average. Average is a word you hear in the average rate of change. It's an application of derivatives. So what?
Hello, can you hear me?
I can't hear you. Now I can.
Oh, okay. Sorry. I guess I just cut out.
Okay. You're still muted. So tell me what the mean value theorem is. What's-
I was just saying that it shows that like over a given interval it's equal to the average rate of change.
What is it equal to the average rate of change?
Um, I'm not sure. I forgot.
Instantaneous rate of change.
Oh, the instantaneous rate of change. Sorry.
Okay. Suhabi. What is zero times infinity? You said could be,
It could be anything.
yes, and we use L'Hopital's rule. When can we use L'Hopital's rule, Nyla?
We can use it when a limit yields 0/0, or if a limit is infinity over infinity.
Right. And Sarah, when's the inflection point? Correct, how many changes? And Jacob, what's a critical number?
X values where the derivative is 0 or undefined.
That's it. Very good. All right. So what are we talking about? Now we're talking about antiderivatives. Where's my notes? Here we go. So we answered all these questions. How many points do we need? Maths and language. It's awesome. We did optimization. Optimization is cool. Derivatives is optimization is a application of derivatives. Not related rates. I'm not even going to talk about this. You can read about it. It's logarithmic differentiation. It's just taking a log first and then differentiating. I don't even want to talk about it. It's used to solve for something. We have a function raised to a function. You take the log of both sides and then you can bring the function down. So by taking the natural log of both sides, you bring the x down and then you have an equation and then you just use implicit differentiation. I guess I am talking about it. I just don't have any assignments for you to do. So nothing, no implicit differentiations. The y equals 3 to the x is a good application of it, but use your formula. All right. Where's my, so that was optimization. That's that. Let's go to mod 0 and pick up antiderivatives. Indefinite integrals. Okay. That's a review of optimization. Where's my blue page? Sorry, just zooming on through. Okay, blue page, lecture on antiderivatives. So the derivative of x cubed plus c gives you 3x squared. To undo it, we invent something called the integral, and it looks like that squiggly. That's called an integral symbol. Okay? It's the first time you've seen it, yes? Looks like a big capital S. Well, or long skinny S. Anyway, let me show you where it is on indefinite integral. Nope, there's nothing in here. I think it's in the other one. On maybe it is on this one. Indefinite, yes, it is. But the reason why it's gonna be on your midterm is because it's pretty easy. Everything's logging up there. I'm having a bad day. Bear with me while my day sucks. I would love to want to cancel class and just no, because I have to do this indefinite integral here. So indefinite integral looks like that. The way I get it on Desmos is to start typing integral INT, and then it just gives it to me. But you see it has little blank spots there. You have to ignore them. Just for what we're doing, you need to ignore the little squares that show up top and bottom. Okay, that's an indefinite integral. And there's an argument inside, like you were taking the log of something, like it's a function itself. And then there's this thing, there's a differential. So the way you would say this is the integral of f of x dx. Okay? Integral of f of x dx. That dx is just the differential. And you just say dx. Okay? F of x is whatever's inside here, and you might have to say something with parentheses or whatever, and then the integral. Okay, that's the notation. And what does it mean? Where's my notes? It means I'm undoing something. So if I want to undo 3x squared, I put 3x squared in as the argument of the integral. So it's the integral of 3x squared dx. That equals x cubed plus c, a constant. The derivative of a constant would be 0. So you have to understand that if you do the antiderivative of 3x squared, there might have been a constant in there that the derivative threw away. You know what I said when it undoes the derivative, but the derivative makes all numbers go away. Derivative of any constant is 0, so it's not going to show up. So if you undo it, just write the plus c to let us know that there could be a constant in there. Okay? All right. So on Desmos, so when we do the antiderivative of a function, we write, so the little f on the inside is the argument of the function. That's the actual function. Outside, it will create a function like we just did here. So the outside function here, so that function itself is 3x squared. The antiderivative is x cubed. To write this as a function, watch this, this is important. Important because it's going to be confusing otherwise if you're not paying attention when you're not here. Do you see how that's a little f? So that we just say f of x. The capital F, we don't say capital F, we say antiderivative of f. The capital F means the antiderivative. Okay, just like if you had the little minus sign, that would be an inverse function. That capital F doesn't mean just a function, any old function. You'll notice most of the time when we do functions, we use small letters, little g, little f, little h. Sometimes you can use capitals, but you got to be careful because they're specifically used for it. They represent antiderivatives. Okay, so if you see a capital F, you can't just say, so I know people, because this is definitely a question that shows up on your test as a read it. If you just read this, I expect you to say the integral of f of x dx equals the antiderivative of x plus c. If you say, just don't look for a second and listen to what I'm saying. The integral of f of x dx equals f of x dx. I said f of x twice. So you have to be careful not to, so that's why the second one, you have to say the antiderivative of f. Okay. The other integral we have, so that's called an indefinite integral and it means the antiderivative. And that's that. We have a lot to talk about, but that's that. There's going to be another integral that isn't going to be on your test. This is the rest of the course. The other integral is called the definite integral. And it's the one that has the little numbers on the top and bottom. And it has a very specific meaning. So when you write the integral from a to b of f of x dx, that means the area under the curve. between little a and little b. Okay. So calculus was about rates of change. Antiderivatives make sense because we're undoing the instantaneous rate of change. Fine, like maybe we're trying to find a position function, fine. But why is the same notation used for something completely different? The area under the curve is using the exact same integral notation, except there's numbers on it this time. Okay, so I'm just going to spoil the story for you. There is a relation, and it's called the fundamental theorem of calculus. Okay, there's only one fundamental theorem in this entire course. In pre-calculus, there was only one fundamental theorem also. It's the fundamental theorem of algebra, but this is the fundamental theorem of calculus. And it's why that there is a relationship between the area under the curve and the antiderivative. And we're going to spend the rest of the course exploring that. But we're not doing that today. And none of that's going to be on this test. What's going to be on this test is you finding an antiderivative. So if you have something like an indefinite integral of x squared, or of 2x dx could be x squared plus a constant. Okay? All right. Let me, so here's some things we know. We know that the derivative of e to the x is e to the x, so the antiderivative of e to the x is e to the x. We know that the derivative of natural log of x is 1 over x. So the integral of 1 over x dx is the natural log of x plus c. So I'm just going backwards. I know when I know the derivative of e to the x is e to the x, then I know the antiderivative goes this way. The derivative of natural log gives me this, so the antiderivative gives me that. In the green, that's the natural log of x. ln. Here's the antiderivative of cosine is sine. The derivative of cosine is minus sine. The antiderivative is positive. The antiderivative of sine is minus the cosine. Okay, this is because we know these derivatives. Okay, don't worry about natural log of x. You can read about it somewhere else. Okay. So how do you do an antiderivative that's a power? So you have the power rule. You know, you bring a number down and subtract 1 from it. The antiderivative of a power, like x to the 1/2, is instead of dropping a power, it's going to add a power. So derivative takes a power away. Antiderivative adds a power. And then the other thing that it does, whatever this 1/2 plus 1 is, when you do the derivative, that would have been brought down. But since it's not there, we just put this in the denominator. So the antiderivative of x to the 1/2 is x to the 3/2 divided by 3/2. Okay, if I take the derivative of this, I'll end up getting x to the 1/2. X to the 5/2, that's going to be, when I add 1, it'll be x to the 7/2 divided by 7/2. Okay. The antiderivative of 2x is 2. What's the antiderivative of x? The first, it's x squared over, there should be a 2 here. It's missing. Okay. All right. But if you have some ugly thing, you have to take the antiderivative of. All you have to do is distribute this, and then you see just 2 powers. You see an x squared and a 7x 1/2. So you could take the antiderivative of x squared, and that becomes x cubed over 3. And you could take the antiderivative of 7x to the 1/2. Since it's a constant, 7, you just take that. That just, remember with the derivative, the constant just stayed there. With the antiderivative, the constant just stays there. Just leave the 7 and deal with the x to the 1/2. X to the 1/2 is going to be x to the 3/2 over 3/2. Once you finish all the antiderivatives, you'll do plus c. Okay, so let's look at the ones you have for homework for a second rather than explore this to any great depths. Where did I put your homework problems? Didn't I have them open? All right, here we go. So the first thing is something like this. All right, I don't know what that picture is. Oh, there's a picture of it. That's what it. Okay, that's what it looks like. If you don't put it in decimals, you see there's no there's no spots there. We're saving that later for definite intervals, but that's the same problem just as a picture. Okay. Now the question is, how do we find the antiderivative of this? Okay, so the first thing we'll do, if you have the derivative of a bunch of things added together, you could just do the derivative of each part. Well, if you're undoing it, you could do the same thing. You could undo each part. So the first thing I'm going to do, I'll copy this down, is I'm going to say, okay, I can break this up into two integrals. I'm just going to do minus. Okay, there we go. So I can break this up into two integrals. Okay. One of them is this 2 cosine x dx. The other one is minus 81. The next thing I can do, remember if you had a constant, it just hung around, I can take that constant out. That's the only thing I can take out of an integral. It's a constant like that. Can't take the cosine out, just the 2. Okay. I can also take out the 81 if I want to. I think I will. Okay, now I have to answer this question. What's the antiderivative of cosine? Okay, sine. Okay. All right. One thing I can do is just check it. What's the derivative of sine? It's cosine. Okay, good. So you have to be able to keep it straight. What's the derivative and what's the antiderivative? All right. Then I have minus 81. What's the antiderivative of the differential? Okay, so the differential is, I'm just going to take the derivative with respect to nothing. And then the integral is just going to undo that. So when you have two things that undo each other, you end up getting just the identity. Nothing has changed. It's not 0. If you had 0, then something would have been like a derivative of a constant would have been 0. But what you're getting here is just the identity, which is just 1. That. So the antiderivative of 81 dx is just 81. Oh, I'm sorry, that's not right. 81x. Now I'll take the derivative of that. You know why I knew that was wrong? Because I took the derivative of 81 and I got 0. I was like, that can't be right. What's the derivative of 81x? What's the derivative of 81x? Anyone at home? Calling on you. No. No, I said, what's the derivative of 8? I'm sorry, what's the derivative of 81? Derivative of 81x. You're trying to do antiderivative. That's a very good point. What's the derivative? Who haven't I heard yet? Who would like to volunteer? Mahir. No, maybe not. Mahir, what's the derivative of 81x? Not the antiderivative. All along, if you saw 80, what's the derivative of x squared, Mahir?
X.
2x. But okay. What's the derivative of 2x? Anusha, what's the derivative of 2x?
Would it be 2?
Yeah, so the derivative of 2x is 2. What's the derivative of 81x? If the derivative of 2x is 2,
81.
thank you, it's 81, Dion. So the derivative of 81x is going to give you that 81. That's inside the interval right there, 81. Okay? So the derivative, so if I took the derivative of x and then I took the antiderivative of it, those would cancel out, and what I'm left with is the x. Okay? All right, one last thing. Always end these with plus c. And you're done. Okay. Doing something like this requires a little algebra. Antiderivative of that. This says the antiderivative of this. This is going to require that power rule that I just showed you. So let's try it. Putting these in parentheses so that it's not confusing. Okay, so what's the first thing I can do with this one? Separate it. I'm going to separate it into this. Oop. Plus separate it into that. Okay. Oops. Okay, so now I've separated it. Now what? I could take the 4 in front and the 6 in front, so I don't have to worry about those. Take the 4 out. Put it in front. Take the 6 out. Put it in front. Okay, now, what's the antiderivative of cosine? I already asked you what that was. Is it negative sine? No, I think it's just sine. The derivative. If derivative of cosine is minus sine, I think this is just sine, but. Right? And now power, what's x to the 6th? So I didn't do the power rule yet, but what did I tell you to do with the power rule? Add 1, so it'd be x raised to the 7th, but when you take the derivative of that, you bring that 7 down, you need to get rid of it. So you need to divide it by 7. And then plus constant. Okay. Any questions on that? That's as hard as your exam questions can get. Okay. There's nothing on your test that isn't basically an antiderivative of a cosine or trig function that you know, and a power rule. That's the worst you'll see on the midterm. There's so much worse. That's why we have the rest of the semester to deal with the so much worse. And I just want to say, the area under the curve is a huge, huge thing. It's really important in a lot of things, and it's going to be a very powerful tool for us to find the area under curve. So antiderivatives, okay. Area under the curves, awesome. All right. What am I doing? So that's, let me get back to my indefinite intervals. Okay, so those are the only ones we have homework for. Let me see what else I have in my notes, because I know I have harder stuff in my notes. Look, it says starting a new topic of importance. That's what antiderivatives are. They're very important. Okay. Evaluate here. So what's the antiderivative of 5 sine of x? What's the antiderivative of sine? negative cosine. And the 5 just hangs around. What's the antiderivative of 9x to the 9th? We'll just leave the 9. What's the antiderivative of x to the 9th? X to the 10th over 10. Right. What's the antiderivative of 7? Let me put it this way so you can't see the answer. What's the antiderivative of 7 cosine x? 7 sine x. And what's the derivative of minus 80? Antiderivative of minus 84. Minus 84. Antiderivative. It's what? It's minus 84x. And don't forget, there's a plus c at the end. Minus 84 plus c. Always put a plus c in. And then you can check it by taking the derivative. If you take the derivative of that, you get 7 cosine x minus 84. Huh? Okay, this one we're not doing. If you look at the notes, it appears it's just out of place, but I'll tell you about it. It's an antiderivative with the sine of 9x. There's a 9x on the inside. So you remember how we had the chain rule? We're gonna have to undo the chain rule. That's gonna be fun. Okay, none of that's on your test this time, but it's gonna be on the final. All right. That's it. This is review for what? Oh, this is midterm review stuff. So let's take a look at these and see if we feel like doing them. I removed a lot of these. I don't think I do the local linear approximation to the sine of 1/2. Can you tell me how to do a local linearization of 1/2? Hold on. This is just a midterm review. Your midterm is the end of next week, right? So everything we're doing today up to antiderivatives is on your test. It's Friday and Saturday, isn't it? Did you make me say Friday? Okay, so any of these topics could be on the test, but let's just check if they say the sine, a linear approximation is this formula. I believe it's in your notes, just like this. That is a line from a function. So our function in this case would be, if you want the sine of 1/2, it would be what? F of x equals sine. Okay. And you want the sine of 1/2. So where do you want to make your local linear approximation? What's a number near sine you could do that's like 1/2? Sine of, remember those special angles? Sine of, remember these from pre-calculus? The sine of 0 was special. The sine of pi over 6. Isn't that near 1/2, pi over 6? Isn't pi, no, just pi over 6 is near 1/2. That's 0.52. That's good enough. So we're going to do our local linear approximation at a equals, so we're going to take this formula. Okay, and we're going to, for a, we're going to put in pi over 6 plus. Okay, now you see the tangent line, and it graphed it very nicely, and it at 1/2, it's very close to 1/2. So now if I use this L of x, let me turn this one off. If I use this L of x to do L of 1/2, that's the approximation I get, 0.479, blah, 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 blah. What's the actual sine of 1/2? 0.479, but are these close? Yep, real close. All right, next one. So you won't get this local linear approximation because it's kind of nasty. You won't, this is a related rate problem. I think I removed this one from the test too. I really only asked for related rate. I only asked that car problem and maybe something that has to do with money. Not this one. Here's another related rate that I don't use anymore. This is a lot of reading. I wouldn't put, by the way, I wouldn't put questions that have a lot of reading on the test. So if you don't like a lot of reading, then you should be happy. Newton's method. Do you remember Newton's method? This is not a lot of reading. It is fun. So how do I use Newton's method to approximate this answer to 6 decimal places? What do I do? I need it to 6 decimal places. I need to take x cubed, so I got to copy this down into decimals. What? I think it's because I put it into decimals. I just wanted to do it again, but it's okay. I didn't do it enough. This would be wrong. This might be wrong. You put it into decimals, you get an answer. You look for the 0, and then you plug it into the Newton's method formula, which is the guess minus the function evaluated the guess divided by the derivative of the guess, and it'll give you a new answer. And if it's the same, you're done. So it's the same, we're done. Remember Newton's method? Yes? I'm going to ask it. I love Newton's method. It's a lot harder on the calculator. Concave up, concave down. What's that all about? So what's that mean? What's that mean? I have this ugly function here. Look at it. Oh, it's nasty. Let's 14x to the 4/3 plus 8x raised to the 1/3. All right, so what am I going to do there? What am I asked for? What's it asking me for here? Suhave, what is it asking me for?
Like like what it says in the question.
Yeah,
Like it's asking you where like where is concave up and concave down.
Right. So what do I need to do in Desmos to find that out? I put the function in. I'm looking at a graph of the function, but I need to know when is it concave up and when is it concave down. How do I figure that out? What am I looking for? What mathematical thing am I looking for to do? To find concavity, I find it how? Which derivative? Second derivative. So I don't think I can do y double prime. I don't think it'll do that. So I have to make it a function. So let's just say f double prime of x. Uh-oh. We have a function in there. So we'll call this g of x. We'll call this g double prime of x. Okay, I found the second derivative. What's that tell me? What am I looking for when the second derivative is what? 0, which would be like there. Anything else? I don't know, but right here, the second derivative is positive. Then it's 0 and then it's negative, right? And what's it over here? No, it's positive. It's positive, then it's negative, then it's positive. It should be concave up. So the original graph is concave up. Then somewhere around here, it changes to concave down, and then it turns back around to concave up. Okay, so I need to find these 2 points. One of them is right there, fine. Where's the other one? I know the sign is changing. I don't know. Remember with the critical points? Who answered that question on critical points? Don't remember. Mahir, were you the person who answered the question on critical points? What's the condition for critical points? What do I have to do? All right, I'm gonna find you, and then you're gonna answer this question. The longer I take to find you, the more I want a good answer. I asked you what were critical points. Jacob, it's you. What are the 2 conditions for finding critical point? What values?
Yes.
No. The X value, no. The something is 0 or undefined. It's not the X values. It's the something, the name of the test. The critical numbers are when the
value where the derivative.
the derivative equals 0. So the X values are the X numbers when the derivative is 0 or undefined. And Sarah, when can concavity change? When can it go from concave up to concave? So something goes from positive to negative. That could happen either if it passes through a 0, or maybe if it's undefined. There's like a vertical asymptote there. Graphs change all the time that way. They go, if it's not continuous. There was that theorem we talked about a little bit, the intermediate value theorem. It goes from positive to negative, it goes to 0. But it can also go from positive to negative if it's not continuous. Okay, so it could be a vertical asymptote. So let's go back to our graph here. Is there a time when the second derivative isn't defined? The first derivative looks like it's defined everywhere. Oh, is it defined everywhere? Yeah, it's defined everywhere. The first derivative is defined everywhere, but the derivative of the derivative is not. Look at this right here. That is a very steep slope. So it might not be defined, and so it isn't. So the derivative of the derivative is not defined, and I think it happens at 0. So if I put a 0 in here, it says undefined. If I put 0.001 in, it's fine. If I put minus 0.001 in, it's fine. Okay, so just like the critical points, the answer here is 0 and the other number, which is, what was the other number? Oh, so I was graphing it here. The other number is this one right here, 0.2851. I would love to get that as a fraction, but I don't think I can. Sometimes you can't. It's that number. It can't be that number. Anyway, that's when the second derivative. So if you want, when it's concave up, you want that. It's concave up everywhere that's where that black region is. Okay, going concave down. Now it's everywhere the black region. Gray region. Okay. That number, by the way, if you really want to work at it, has something to do with the numbers 17 and 13. So, all right. How about a graph like this? When is this concave down? What am I going to do with that function? I put it into Desmos and I'll say, and I'll do what? Concave down. What am I looking for?
No, the maximum. Maximum, yeah, because it's down, isn't it? And this is
Yeah, but I want more than just the maximum. Yes, what you're saying is right. Where it's a maximum, it's concave down. So you can see that there's a maximum there and it's concave down, but it's concave down all around it too. Not just at the maximum, it's everywhere. So it's what? It's another, which one? Second derivative, yeah. You take the second derivative and say it's less than 0, and that'll tell you the answer. So here, you could, but this one is particularly easy. If you actually took the second derivative, you end up with 12x plus 42. And that's when you say less than 0, you could just solve that and get x is less than minus 7 over 2. Okay. I don't know. Somehow my thing's just changing on its own. Find the critical numbers, then use the second derivative test. So how do we find the critical numbers? Go ahead, Jake, tell me how to find critical numbers.
It's when the derivative of x is equal to 0 or undefined.
So I take this function and I take the derivative and I set it equal to 0 and I end up getting two answers, 0 and negative 21 over 4. That is, it's use the second derivative test. So I must find the second derivative, which is this number right here, or this function right here. That's the second derivative. And then I just plug 0 in and I plug minus 21 over 4. When I plug 0 in, I get the second derivative is 0. What does that tell you if the second derivative is 0? Is it a maximum or minimum? Second derivative would have to be negative for a maximum and positive for minimum. So if it's 0, it's nothing. Oh, man, probably. Probably, not sure, but probably. It doesn't, no guarantee it's an inflection point. If the second derivative is 0, it could be an inflection point. Thank you, Sarah. But what about the other one? When I plug negative 21 over 4 in, I end up getting a positive number. So what would that tell you? If negative 20, if the second derivative is positive, it's concave up, and it's a minimum or maximum. So what did they ask you here? It says find all criticals and use the second derivative to determine all local extrema. So we did the second derivative test. We just found that there's a local minimum. Look, doesn't it actually even just tells us the local minimum is what? Minus 21. Okay. Let's get back into our group work then. Did we finish our group work from last time? You did? You found all the maximums and critical points. Did everyone finish everything? It's all done. All right, well then we can move on to the next topic. Actually, I'll look at it first because I don't believe you. It's not due until Monday though, but it would be nice if it were done now. Is this your class? It's not your class. Let's just fix this. Devon. Devon's graph has a what? What do I see? Just looking at it, what do I see? Maximum, a minimum, inflection point? Devon, what do you have on this graph? When you saw it, you were excited because it has a what and a what? Go, Devon. Okay.
Sorry, what was the question, Professor?
I was just asking you you produced this because I asked you to give me a function that had both a minimum, a maximum, a minimum or maximum, and an inflection point. Do you have that here?
Did it not post?
Yes,
Sorry.
you did. I was asking you to say yes or no. Do you see the maximum in? That's the easy one.
Yeah. Yes.
That's interesting. Look at this. I didn't realize I could do this on your posting. Did you see that? I didn't know I could do that. Anyway, this inflection point somewhere around here, around 5, and another one here around 20, maybe.
Is that the actual post or the preview?
I don't know what that is. Honestly, let's go back to this. I clicked on, so here's the post. You could
Yeah.
just click on it. And there's the Desmos graph, but it's something showing up right here. I don't know what it is. I don't know.
Yeah, that I don't know. I think that's the preview, but the post is above it.
It's still pretty cool. You gotta admit, I'm sitting here, I'm doing this and it's giving me numbers. Okay? And I can open up your post. Preview looks good. Anyway, so Sarah says, actually, Nana's gonna say what Sarah says.
According to the quarter compression, inflection points are at 5 and 20 hours.
5 and 20. That looks good. Thank you, Dana. And Jake says,
According to the quarter progression, there is a minimum percent gain at minus 1.9 hours.
is it about taking a test? Is it?
It's about our grade.
Right, so you might want to say that's minus 1.9 hours. Okay. So Nyla says the minimum says, you see, this F prime of minus 1.9 is 0. F double prime is positive, that makes it a minimum. The inflection points, she has both this second derivatives equal to 0. Okay. Any questions on that? That looks good. Thank you, Nana. Okay, Kara. Kara's not here. Okay. Can I do her? No, see, now I can't do anything on hers. And nobody replied to her. So let me ask the rest of the class, not in Kara's group. Do you see any max and mins on this, on the red graph? Do you see a max and min on the red graph? Who's in this group that could answer this question? Mahir and Suhabi and Anusha, these are, you all didn't do this. So you got to get on the ball, but are there max and mins in this? So we'll start with Mahir. Mahir, do you see max and mins?
Yeah, maximum, like, the one,
What's that right there?
that's a minimum.
Right, so right there's a minimum. How about this?
That's a maximum.
Okay. And then,
And that's a minimum.
okay, so you just have to identify those 3 max and mins. Did she give you those points where they are? One of them is around 50,000, one's a little over 100, like 115,000, and the other one's 200,000. Did she give you those things? I think she did. I think she did. Fine. Oh. How did I get kicked out? All the way out. That's what I got. Yeah, I see. Kara's post actually has a lot of data points. Here they are. You see them all? So, Mahir, Are you there?
Yes.
All right, we determined that there was a minimum around here. So which one of those on the table is a minimum?
Um,
X value gives you a minimum.
53.
53 is the minimum, correct?
Gotcha.
Okay, how about the maximum? Here's the maximum, where's that? At what value?
100.
What?
It's at 100.
No, I think it's 114.
114.
I think we're somewhere near there. Okay, how about this minimum? Where's that about?
117 or 171 or wait, yeah, 210.
Okay, in all of those cases, this derivative is 0, this derivative is 0, this derivative is 0. Okay, that's why they're max and min derivatives are 0. Do you see any inflection points? Should be one here, and there should be another one around there. Looks like that one might be 100, maybe. And maybe this one is, gosh, near 150 or 60 or something. Okay, so here's a 0 in the second derivative. So that's 171. So that's a inflection point. And here's another 0 at 80. That one must be another inflection point. Okay. Inflection points give you zeros for second derivative. All right. Can you write these things down? Because they have to be done by next week. And I really want to do other things next week besides work on these. So try to finish that up. So the group's done. And I'm just going to talk about what's the next thing. So if we broke up into groups, if we did break up into groups, we would be talking about our individual projects. What? Yes. Oh, let's talk about it. Okay. So mod 8 isn't open yet, because I'm not probably going to open it until the midterm's done. But in mod 8, the discussion is called proposal. Give a proposal for your independent research project that you might want to explore. Oh, you will be doing this in class. So this is what you need to do. So it's a lot harder. Before it was just a proposal. Now it's since you actually have a project, you're going to have to propose it. Oh no. And here's the things I require for a proposal. I require that it be interesting, relevant, and informative. That's the first most important thing. Do not post boring stuff. Population, boring. You know that BFF one, the example of the BFFs that Kara did? That was a student project. They asked so many of their friends what their salary was and how many friends they had, how many BFFs they had. And by the way, it wasn't BFFs, but let's just pretend it was. Okay. So that's what somebody did as a project. I've had a lot of neat projects over the years. Ideas are on my website. Well, there's any sort, if you're interested in Tesla stock or Apple stock was popular at one point, if you're a business major, I might believe that that's interesting and relevant and informative because you're going to tell me something about the stock. Okay, salary and BFFs, people wanted to know how many BFFs they had. Salary made a difference. So they asked people. Grades from studying, I think I made that up. I honestly think that was not real. Drug stability, though, when I worked for a pharmaceutical company, that was what they wanted us to do all the time, was drug stability studies. So that's useful. If you work for a pharmaceutical company, Sarah, do you work for a pharmaceutical company? If you did, you wouldn't be taking calculus at a community college. You would what? You were, that's why you're taking calculus, because you don't want to work there for the rest of your life. Correct. Height and weight. That one, I had a lot of fun with height and weight. When I was at Rutgers, I taught a class that was almost entirely football players. I know, it was so weird. Nobody warned me. All I walk in and there's these guys, and they're all giants. And I'm doing this height weight example, and I was so skinny compared to the rest of them. That was the first time I felt thin. Because there were a lot of them that are like, I'm 5'2" and 300 pounds. I'm like, oh, that's going to throw up my data. Okay. So they were huge guys. Anyway, and you know, so here's a sad story that one of those football players failed that class. And they didn't kick him off the football team until the middle of his senior year. He was like a star player, and they kicked him off the football team because he failed my math class in his freshman year. And that Rutgers got in trouble for it. You're not allowed to, can't have failures if you're a football player. It was very sad. I was like, no. He was a really good player too. But Rutgers was losing big time back then. So, all right, here's one, world population. I think that's boring. Do you have any reason to find the world population interesting? No, never. So don't do that. Okay, but somewhere in here I have old materials. Okay, regression projects, ideas from the past. Okay. No, it's worse. You can steal the idea, but you have to get the data.
Oh, we do.
Oh yeah, you have to get the data down. That's so much easier than you think. The number of abortions. Oh, number of abortions in the US. By the way, these are long before Roe versus Wade was overturned, but yes. Divorce rates. I could see where people might be interested in divorce rates. Oh, by the way, sometimes, so in 2008, I've been doing this for a long time. In 2008, the economy was really bad, and every single topic was like death, how many people died, how many people died from poison, how many people died from medications, how many people died from, like, every single person tell you had death as a topic. Let's not do that. We need happier topics, but divorce rate is something. Percent of condoms being used worldwide. Price of gold. People getting HIV. Oh, that was 1 year the students thought they would be clever. People dying from HIV was one student's topic. Another student was people dying from another sexually transmitted disease. And then another person picked another sexually transmitted. So it was just kind of boring because it was all sexually transmitted disease. But they thought they were being clever. You need 9 data points. Alcohol-related deaths, salary. I know people, one woman did salary of vets. She wanted to be a vet. She looked at the salaries of vets. She changed her major to pre-med. She's probably a doctor now. There's one guy who asked me for letter recommendation. So here's the nice, so why am I making you do this topic? Just picking on me. Some of you sometimes will ask me to write a letter of recommendation. Sometimes this happens. Rarely does it happen, but it happens. You should never ask a math professor for a letter of recommendation, by the way. Ask an English professor or humanities, because they write better letters. Anyway, if you ask me to write a letter and I don't have enough to write about you, I'm not going to just say you got an A in my class, because that's horrible. Because my letter's not going to be as good as an English professor anyway. And English professors get to talk to you, they interact with you, yada, yada, yada. So what I do is I can talk about how you work in groups, because you work in groups, how you present your data. I can talk about various things I have going that I can write a recommendation of. But if you do your own research project, I get to say that in a letter of recommendation. And let me tell you something. When I was doing this before, some of my students were getting really good not jobs, but one of my students got into Yale Medical School. And it was mostly, I mean, he was a really bright kid, but he did one of these projects. His project was about populations. He studied some animal population over time, and he talked about when they were, at what point they hit an inflection point, and when they were going to go extinct. You know, that it was a bad time for them. And this other student did another student got an interview with the University of Pennsylvania to go to graduate school there. He did the condoms one. It was very interesting. Give me something to write about. I can write something. That's why I wanted to be interesting, because if you do population of New Jersey, it's really boring. Somebody was a real estate agent and they did the population of New Jersey, and that was at least more interesting because that was why they cared. But you can pick other things besides pregnancies and federal minimum wage. These are kind of boring. Honestly, these topics are kind of boring. Not that I look at them. Teachers in middle school, the growth of Coca-Cola, tuition growth over time, deaths by poisoning, hardware sales. Oh, so it is nice if you work for a store. If you get sales data, that's nice, but 9 days worth of sales data you have to get. Right, these are kind of some of these topics, they're topics, but I really, any topic having to do with celebrity. So who's that guy from One Direction who died?
Yeah,
Do you know him?
not personally, but yeah, it's a One Direction. He died.
He was like 31 or something.
Yeah, he fell out of the.
It was only a 3rd-story balcony.
Yeah.
I know. I expect when people fall on the balcony, it's like one of those Hawaii balconies that are way up high. But a 3rd-floor balcony is not, it's not, you could survive that. What? I know, the nerve
He
of him. Anyway, if you want to track sales of some famous celebrity, did you see what's her name? Who was on Saturday Night Live, the musician on Saturday Night Live last Saturday? No. One from Fleetwood Mac. I know, she's an old singer. What's her name? She was on Saturday Night Live last Saturday. Who was that on Saturday Night Live last Saturday? No, it was. I can't remember her name. Anyway, if you're interested in any celebrities and you want to track their success, I'm really fine with that. How many home runs Babe Ruth hit in the 40s is not so interesting. Who else died? Pete Rose died. Remember him? He was a Phillies. No. I don't know anybody. Tell me somebody that died. How?
The guy from Friends died.
Yes, he died too. I know, and there's a lot of people dying, actually. I tracked that, unfortunately, because I'm depressed, but
Oh,
still. Because you guys pick depressing topics. Find somebody who's doing well. Basketball players. People track basketball players. People have tracked video games and found the number of users to video games. People have tracked. What are you guys interested in? Do you have any interest at all? I'm going to call on somebody at home. Nyla, what are you interested in that you could possibly get data from?
Um, I don't have anything specific yet, but I'd probably do something, um, I don't know. I'm still deciding whether it'd be like something scientific, like recording, like getting the data from like, I don't know, uh for every like field of science, how many, like women are in that field or something like that, or doing something.
Don't do every field, just pick one field, like chemistry or something. And
Okay.
track the number of women in chemistry over the years. You can probably get that data. If you just, all you have to do to get data is Google it. The data should be around. Some of this data is around. You just have to make sure you get 9 data points. So 9 years or decades or whatever.
Okay.
But that's a good topic. I like that. Women in science is good one. Suhabi, what are you interested in?
I'm kind of interested in the teachers in like elementary and middle school.
Salaries, or how many of them there are? How many jobs there'll be? Any of those are good, by the way. Stay away from topics you can't do, like how awesome people are.
So it's stuff that's facts to it.
Subjective stuff or colors, or even stay away from rankings of colleges. That's so subjective. There's no such thing as, if you get to the population of the college. I used to say this thing. So if you go to a bar, you're not old enough to go to a bar, but maybe you'll go to where do you guys go where there might be cute people? To meet, not. Okay, actually, I'm going to modernize it. Forget the boardwalk, although boardwalk is very good. I'm going to take you to the social media. So you're scanning social media, and let's say you go through and you count the number of cute people on social media. So you sit there and you count, and then you go back an hour later and you count to see if there's more people, cute people on social media. The problem is, what you discover is that it's so subjective that the same person that came up the first time as not cute, the second time you might pick is cute. And the reason why bar is a good example is because bar has a solution. Why is that? Because when you're at a bar drinking, you get these things called beer goggles. Have you ever looked at that? Yes, that doesn't happen. No, but beer goggles mean that you are drinking, and so you see things through beer goggles. So now people who weren't cute before look cute now because you're drunk. Okay, that's what a beer goggle is. I taught you some bad term. I'm sorry. But yes, you can't measure how cute people are, but you can measure how many cute people there are and compare how sober you are. But you have to have a way of measuring how sober you are. So, what? I had somebody do specularized their chest on their whole family at Thanksgiving. It was kind of funny. One of their relatives was a cop, so he borrowed a breathalyzer and he did breathalyzer. So, it was measurable. But try to stay away from sanity, by the way. That I know I've had a lot of arguments with students that want to do sanity, because I know we're all depressed, but there's no really good, the ways that they have for measuring sanity are not great. Like how many, does it matter how many psychoses you have if one of them is really bad? Do you know what I'm saying? You can't compare them. You are a mass murderer, but you also have ADHD. I kind of feel like one of them outdoes the other. What's not mass murderers? What's that? The psychotic? And if you're a psychotic killer and you have ADHD, those are not comparable at all. Okay. And if you're psychotic, but you live in a nice suburban neighborhood and you don't kill anybody, then maybe that's fine. Lucky you. So anyway, try to stay away from mental illness unless you have a real good way of measuring it, but they got to be numbers. Anyway, next week, I'm going to spend all week reviewing for the midterm. Okay, so we're going to finish 7, which is on the midterm, and then 8, because the quiz for 8 is actually the week after. So I'm not gonna do much except review. So try not to miss class next week. Good luck. Have a good weekend. Talk to you next week. Bye-bye.
Hi, thank you.
No problem. Have a good night.
You too.
I have a question.
Guys. Nina?
For my quiz I took on Tuesday, I forgot, there was like a problem we had to like measure the maximum and the minimum, or find maximum and minimum. And I don't know if I did it wrong, or I feel like I did it right. It counted me as wrong. So I don't know if it's because like I'm supposed to
Okay, Nina, let me stop sharing